Hi, welcome to our next unit on forces. And so our first screencast is going to be on forces and Newton's laws of motion. Okay, so a force is something that is absolutely crucially important in AP Physics 1. We're going to talk about them for the rest of the year, and they're essential for understanding mechanics, the physics of motion. So the idea is this: a force is simply any push or pull that acts on an object. And the thing about force that's most important to understand is it takes a force in order to make an object accelerate. If there is an overall force acting on an object, then that force is going to accelerate. If an object is accelerating, that is because there is an overall force acting on it. Now, it doesn't take a force to make an object move. An object can move at a constant velocity as long as it's not accelerating. But if there is an overall force on it, it's going to accelerate. So just take a look at here. I've got a force. I've got an object sitting on the floor, and it's at rest, and it's going to stay at rest unless at a velocity of zero, unless a force is applied to it. So now this person is going to apply a force to the object. So they're pushing on the box. Well, that's going to cause it to accelerate. Now, if the person stops applying force, then the object is not going to accelerate anymore, but that means it's going to continue to move at a constant velocity. Now, we're ignoring any other sources of forces that might be acting on this object. So keep in mind that it takes a force to make it move, to make it accelerate, but an object can move without accelerating in the absence of force. Now, we're obviously going to have to measure forces, and the units we use for measuring forces is the Newton, named after Sir Isaac Newton, who basically invented classic physics, including the concept of force. So, our definition of 1 Newton will be this: 1 Newton of force, which we use the capital N as our abbreviation, is equal to the amount of force necessary to make 1 kilogram of matter accelerate at a rate of 1 meter per second squared. So, that is by definition what a Newton is. So, another thing we need to know about forces is they are vector quantities. The direction matters, and we have to keep that in mind when we're looking at them. And the main thing to know about force vectors is since forces cause acceleration, the direction of the net or overall force acting on an object, and I said because there's often more than one force acting on an object, but when I look at the sum of all the forces, the overall force acting on the object, whatever the direction of that overall force is, that is the direction of acceleration. So the direction of the force vector is the direction of the acceleration vector. All right, so let's take a look at this. I have an object that's at rest. No force, no acceleration. A force in the positive direction is applied to it, so therefore the object is going to begin to accelerate in the positive direction. And as long as that force is applied in the positive direction while the object moves in a positive direction, it will continue to gain speed in the positive direction. But if the force is then directed in the opposite direction, now remember, whatever the direction of the force is, that is the direction of the acceleration vector. So now I have the object, its velocity vector is pointing in the positive direction, but the force vector and therefore the acceleration vector is pointing in the negative direction. So therefore the object is going to slow down, eventually stop, and then go in the negative direction. So here I just have some examples of this. I don't know if you need it or not, but here you go. Velocity, I have a high velocity in the positive direction, but I apply a negative force. Therefore, I'm going to have a negative acceleration. The object is going to slow down. Eventually, it will stop. And as long as that force continues to act in the negative direction, the object will then begin to pick up speed at going faster and faster in the negative direction. Conversely, if the object is traveling in the negative direction, I apply a positive force, the object is going to slow down, still traveling in the negative direction. And since the force is now in the positive direction, eventually the object will stop. It will start to pick up speed in the positive direction. But then if I remove that force, it will just continue to move at a constant speed without acceleration in that positive direction. Now let's talk about Newton's laws of motion. You've probably heard about these, but we do need to go over them. Okay, so Newton's first law of motion, simply stated, says that an object at rest is going to remain at rest, and an object in motion is going to remain in motion unless it's acted upon by an outside force or an external force. So what do we mean by that external force? Let's just start off with that. So what we mean is this. Okay, we already said if you apply a force to an object, it should accelerate. However, it is worth noting that force needs to be external for reasons we're going to get to in a minute. No, let's just get to it right now. Here's the deal. A force is something that needs to exist between two objects in order for there to be acceleration. So here I have a bus, and there is no external force on it, so there's no acceleration. So a very strong person comes along and applies an external force. That means this person is not within the bus. And they apply an external force to this bus in the positive direction. Well, it's going to accelerate in the positive direction. However, if instead of the person being external to the bus, the person was internal to the bus, so this force was applied internally, it's not going to cause acceleration. And let's think about it for a second. While the person's hands are pushing the bus in the positive direction, the person's feet will have to push the bus just as hard in the negative direction, and therefore cancel the forces out. So that's what we mean by an external or an outside force. Now, another way of looking at Newton's first law, I should say, it's a commentary on the concept of inertia. Inertia simply is the degree to which an object will resist acceleration. It resists changes in its motion. So the more inertia you have, the less you want to change your velocity. So the thing to keep in mind though is what causes an object to have inertia? It's simply its mass. A bowling ball and a soccer ball. Okay, you run up and kick the soccer ball. It has low mass, it has low inertia, therefore it accelerates easily. It doesn't hurt your foot. But if you ran up and kicked a bowling ball, it has a lot more mass, it has a lot more inertia. It's much more resistant to changing its acceleration, and therefore you're going to have a hurt foot. Now, Newton's second law of motion is the easiest to understand, and it is just one of the most crucially important laws in the physics of mechanics that we're going to be studying all year. So Newton's second law of motion simply says that the acceleration an object experiences is directly proportional to the amount of force applied to the object and inversely proportional to the mass of the object, or therefore the inertia of the object, right? So basically, this is the best way to think of it. More force, more acceleration, more mass, less acceleration. However, we usually write it in this form here. F equals ma, or more appropriately, the sum of the forces equals mass times acceleration. But this is the way we'll usually write it, and it's actually a very convenient way to work it. So it's easiest to understand Newton's second law this way, but it's easiest to apply it this way. So let's just try this here, right? So I have an external force F acting on mass m, and since this force is acting in the positive direction, I'll get acceleration in the positive direction. So F causes mass m to accelerate at rate a. However, if I double the force while leaving the mass the same, since force is directly proportional to acceleration, if I double the force on that mass, I will double the acceleration experienced by that mass. On the other hand, if instead of doubling the force, I had doubled the mass of the object and left the force the same, what I find now is if I double m, since it's inversely proportional to the mass, that the acceleration will now be 1/2 of what it was. It'll be 1 over 2 m, all right? So it'll accelerate half as fast. It's a really easy idea to wrap your head around. But then it gets a little complicated, and that's because there's almost never just a force acting on an object. There's usually multiple forces acting on it, and tomorrow's lesson will all be about how to uh, disambiguate those forces and simplify them and work with them. But for right now, just work with me here. It's best to write Newton's second law of motion this way: that the sum of the forces, this capital sigma means the sum of, just if you add them all up, keeping in mind positive and negatives for directional descriptors, that the sum of all the forces acting on an object causes its mass to accelerate, right? Because there's usually more than one. So look what I'm talking about here. We'll keep it really simple, okay? Sometimes we have what we call balanced forces. When forces are balanced, they cancel each other out. You have just as much negatives as you have positives. So I have a 5 kilogram cart. I apply 10 newtons of force in the positive direction, but someone else applies 10 newtons of force in the negative direction. Well, when you sum up positive 10 newtons and negative 10 newtons, what you get is 0. And since there's 0 force acting on that, is not going to accelerate. That doesn't mean there's no force acting on it. It just means the sum of the forces is 0. It's a slightly nuanced there, right? When we have unbalanced forces, that means they don't cancel out, right? So now I have that 10 Newton force pushing in the positive direction, but now I have some pushing 3 times harder in the negative direction. So now I have positive 10 newtons plus negative 30 newtons. That gives me negative 20 newtons. And therefore, if the mass of the object is 5 kilograms, when I solve for acceleration, I'm going to see it's accelerating in the negative direction at 4 meters per second squared. Again, not very tricky mathematically, but you do have to keep in mind the direction of the vectors acting on it and work with a sum. Now, Newton's third law, I would say, is probably the most misunderstood law in physics. I mean, most people think they understand it. They think, for every action, there's an equal and opposite reaction. That's really not what the third law says, okay? So let's just try to get it right. The best way to think of it is this way: is a force must act between two objects. You can't have a one-way force. So it takes two objects to have a force, and both objects experience the same magnitude of force, but in opposite directions. That's the way to think of it. A force exists between two objects. Both objects experience the same magnitude of force, but in opposite directions. So let's look at this here. I've got object one, a person wearing roller skates, so we take friction out of the equation, and you have mass m, and they're pushing a cart again on rollers, so we can ignore friction. That has mass 2m. Well, the force that acts between these two objects is going to be the same. So there is a force F pushing this cart forward, but there's also force negative F of the cart pushing the man backwards. You can't have more force in one direction than you have in the other. It just doesn't make any sense if you do. You'll see why as we go through this unit. And so what's going to happen then is the person will accelerate faster in the negative direction because he has half the mass than this object accelerates in the forward direction because it has twice the mass. Now let's just talk about the different types of forces. One of the trickiest things in this unit really is learning how to identify the different forces that can act on an object. All right, so let's just go through the biggies, the ones we're mostly going to work with. Okay, let's start with gravitational force. So gravitational force is a force that exists between any two objects in the universe, but for the most part, it's going to be some object that's falling and the Earth. Okay, but it doesn't have to be the Earth, but we'll get more into that later in the year. But for right now, just say it's a downward pointing force. Okay, so it acts in the downward direction. And since F equals ma, we usually refer to it as mg because it causes the object to accelerate at 10 meters per second, which is g, right, little g. So we often just refer to the gravitational force as mg. But keep in mind, it points in the downward direction on an object. Of course, Newton's third law says that means the force on the Earth is upwards, but we're going to ignore that for right now. Then we have what we call the normal force, and that doesn't mean regular force. What that means is perpendicular force. So a normal force is a force that exists between a surface and an object pressing on that surface. So when two surfaces press on each other this way or this way, we call that a normal force. Think of it as it's the force that keeps an object from sinking through the surface of another object. All right. And the thing to keep in mind about it is this is a force that is going to act uh, uh, um, perpendicular to that surface. So if I push this way, it's putting a normal force in that direction. Now let's look at friction force. Friction, again, is a force that exists between two surfaces, but instead of the normal force, which is pushing in perpendicular directions, it is a force that always opposes motion. So it's going to have a tendency to reduce the speed of a moving object because it's going to go against the object's motion, and it always acts parallel to the surface. So whereas the normal force acts perpendicular, the frictional force acts parallel to that surface. Now, the tension force is another one that we're going to deal with a lot. Some of you are going to have a bit of a struggle first wrapping your head around it, but you'll get there. But basically, it's just think of like a rope or a string. Anytime you're pulling on something, it's like I don't know. It's like if I just pull on a rope, in order for my hand is going to apply a force on here by applying a tension force. The thing to keep in mind is if there's 5 newtons of force pulling this way on this end of it, there's 5 newtons pulling this way on the other end of it. That the force is the same on both ends of it. It can't be stronger on one end than the other, ever. Because by definition, tension force exists between two objects, and those two objects are applying a force to each other. Newton's third law tells us equal and opposite forces. And then we just have what we call unapplied force. It's just sort of a catch-all term for, someone's pushing on something or a car is making something. So when acceleration is happening, and it's not really clearly delineated as gravitation, normal, friction, or tension, we're just going to call it unapplied force. So just usually a person applies a force to a car. That's really what we're talking about. All right. Now, let's just go through a couple examples and call it good. Okay, so here's what I've got. I got a 5 kilogram box sitting on the floor of an elevator. We're going to do so many elevator problems, and you're going to love them. Okay, so here's what we got. First of all, what is the gravitational force acting on the box? Well, so the force of gravity is going to be equal to mg. So the force of gravity, F sub g, is going to be equal to mg. And since m is 5 and g is negative 10, the gravitational force acting downwards is going to be negative 50 newtons. But look, the object's not sinking through the floor of the elevator. It's sitting there, right? And since the object is not accelerating, the net force on it must be 0. So therefore, what we know is this, that the sum of the gravitational force and the normal force, F sub n, equals ma. But since a equals 0, then if this is negative 50 and this is 0, we see that the normal force must be 50. In other words, gravity is pulling down 50 newtons this way, and the normal force is pushing perpendicularly upwards with the same amount of force. It's in equal and opposite forces there. But now let's have the elevator accelerating upwards. So now the 4 kilogram box sitting in the floor of an elevator, and that elevator is accelerating upwards at 4 meters per second squared. How do we solve this one? Well, we say, I know that gravitation is pulling downwards on this 5 kilogram box with mg. And mg, we've already determined, is negative 50 newtons. Got a little bit lazy and didn't write my in here. I don't know what the normal force is in this case, uh, but I do know that I have a 5 kilogram object accelerating in the positive direction at 4, so 5, which by the way, mass is a scalar, doesn't have a direction associated with it, and positive 4 because it's accelerating upwards. So this is 20, and when I solve for this, I'm going to get 20 plus 50, and we get 70 newtons. Think about it. Gravity's pulling down on the box with 50 newtons, but the floor is pushing up on the box with 70 newtons, so of course the box is going to accelerate upwards. All right, well, let's try this out. Now I have the same thing, but now the elevator is accelerating downwards. Okay, so same thing applies. So I know that gravity is pulling on this 5 kilogram box with force mg in the negative direction. So negative 50, that's 70 newtons, gravity is pulling down on the box. I'm trying to find out what the normal force action of the box is, but I do know I have a 5 kilogram box, and this time it's accelerating in the negative direction of 4. So when I solve for this part of it, I get negative 20 plus 50, because when I move this over, I get positive 30. It's pushing upwards with 30, while gravity is pulling downwards with 50. So of course the object is going to be accelerating downwards uh, at 4 meters per second squared. Now, if I ask you though, what is the normal force acting downwards on the floor? Well, we know that if the floor is pushing up on the box with 30 newtons, the box must be pushing down on the floor with negative 30 newtons. It has to be equal and opposite forces. We'll have a lot more to say about elevator problems later on in the unit, but they're pretty cool. Listen, thanks for watching this, and I'll see you in class tomorrow.